Hello again, everyone. So let's try and solve this problem for this video. Now this problem is actually from your module 2, the last example that you can see there. So let's directly go and solve this problem. So the key points of the problem is, first, it is a welded lap joint that is under a tensile load. Okay, so it's a welded lap joint under tensile load. So let's go with step 1. Step 1 is to determine which of these members should we analyze. Should it be the plate or should it be the angles? Now if you notice, the plate has a thickness of 3/4 inches while the angles have a thickness of 3/8 inches. Now we have two angles, so basically you might think that the angles might have larger in cross-sectional area. Note that we need to analyze the member with the smaller cross-sectional area. Okay, now if you notice, we do not have additional given for the additional dimensions for the part of the plate here. In other words, we cannot obtain its cross-sectional area since we do not have the value for the dimensions of this part. So in this problem, it is safe to assume that we are to analyze the angles, or the angles is the much more critical steel member in this joint. Okay, since we cannot solve the cross-sectional area of the plate, then it is safe to assume that the angles will have the smaller cross-sectional area. So we need to analyze the angles. Okay, step 2, we solve for the shear lag factor U. Now this is not a plate, it is an angle. So basically we will use U is equal to 1 minus X over L. Now L, we can see from the figure, it is the longitudinal weld. This is the longitudinal weld, this is the transverse weld. Now we'll only get one length of that is 12 inch. So that is your L. Now as for the X is actually the X or Y bar of your to be analyzed member. So the X and the Y bar of the angle. Now this can be obtained in your steel manual PDF. I believe you can get this in page 1-46 to 1-47 in your steel manual PDF. And I think the value over there is 1. No? They have an equal value since this is an equal leg. So we have the X bar and the Y bar is equal to 1, which will result to X is equal to 1 inch. 1 inch in the steel manual PDF. So solving, we now have U is equal to 1 minus 1 inch over 12 inch. This is all equivalent to 1 minus 1 over 12 is equal to 0.917. So 0.917. Okay. Next, we'll go to step 3. Step 3 is we need to get the net area, AN. AN for welded members under tensile load is equivalent, AN is simply equal to AG, or the total gross area. Now, the gross area of one angle, okay, one angle area gross is equivalent to 2.5 inches squared. Now, where did I get the 2.5 inches squared? This can also be obtained in your steel manual PDF. Okay, I believe it's also in the page 1-46 to 1-47. Okay, the area of one angle is 2.5 inches. Now, since we have two angles in this figure, we have 1 and 2, so we'll have a total gross area of times 2. So the net area is equal to the total gross area, which is 2 times 2.5, which is now equal to the net area is equal to 5 inches squared. I repeat, one gross area of one angle is 2.5 inch squared. This is taken from the steel manual PDF. This is for the 3.5 by 3.5 by 3/8 angle bar. Okay, so AN is now 5 inch squared. One angle gross area 2.5, two angles in the given, so that is 2 times 2.5. So we now have our net area. We proceed to step 4. Step 4, we obtain the effective area. The effective area is simply the net area times your shear log factor U. So the we have the AN or the net area is 5 inch squared times the U, shear log factor, we have 0.917. So the effective area is now, have 5 times 0.917, we have 4.585. 4.585 inch squared. So we now have our effective area. We now proceed to step 5. Step 5. For step 5, we need to solve the rupture strength. The rupture strength is simply equal to the rupture stress times your effective area all over 2. Okay? So we have the rupture stress times the effective area divided by 2. The rupture stress is given as, this is FU. Okay? FU, rupture stress. FU is 58. So we have 58 KSI times area effective, no? By 4.585 inch squared divided by 2. So our rupture strength is equal to, we have 58 times 4.585 divided by 2. We have 132.965. The 132.965 skips. Note that this formula for the rupture strength, this is only for the ASD. Okay? We have a different formula for LRFD. We are using ASD because in the question it says use ASD. So in the solution, the ASD or the LRFD will start to affect in your step 5. So we have now the rupture strength. We proceed to step 6. We need to solve the yield strength. Yield strength is equal to yield stress, no, times the the gross area all over 1.67. Okay, I repeat, this formula is for ASD. The Fy times the AG all over 1.67. The yield stress times the gross area all over 1.67. The Fy from the given is 36. 36 times the gross area, that was 5, all over 1.67. So we have our yield strength. Okay, so 36 times 5 divided by 1.67. Okay, we have 107.78. 107.784 kips. Okay. Step 7. Step 7, we need to determine our design strength. So our design strength is simply the lower value of the 2. Now obviously the lower value of the 2 is the yield strength. So we'll have 107.784 kips as our design strength. Okay? So now proceed to step 8. Step 8, we need to solve our ultimate load PU. So PU, to solve it for ASD, that's simply the P dead load plus the P live load. Now the dead load is, from the given, dead load is 50 kips while the live load is 70. So for the formula, that is simply dead load plus live load. I repeat, this is only for ASD. So we have dead load is 50 plus live load is 70. So our ultimate load is 120 kips. Finally, for step 9, we compare. Obviously, the 120 is greater than the 107.784. No? This is the 120, while this is your design strength. Obviously, the PU is greater than the design strength, or 120 is greater than 107. So your ultimate load is greater than design strength. So it means that it is not adequate. meaning the joint will fail once applied with a tensile given load. Okay, not adequate because the PU is greater than your design strength, or your ultimate load is greater than your design strength. That is all.